Hello, welcome to another video on the basics of in vivo NMR. Today it's going to be about MR hardware and in particular about radio frequency coils. So all MR scanners are composed of a magnet, gradients and shims and a radio frequency coil. Now there have been previous videos on the magnets and also a video on gradients and shims, and today's video is going to be about the radio frequency coil. The radio frequency coil has two main functions. The first one is to basically transmit radio frequency pulses that excite and perturb your magnetization. And the second part is to pick up your NMR signal and detect it and process it into MR images or MR spectra. Now there has been quite a bit of time between the current video on RF coils and the previous hardware videos. One of the main reasons is that to understand RF coils, you need quite a bit of knowledge. And now you need to be familiar with terms like resistance, voltage, and currents. But it doesn't just end there. There's many other terms like electric charge, voltage drop, capacitance, inductance, and a whole bunch of symbols as well. So in other words, there is a wide range of knowledge that is required to really understand RF coils. Then the question becomes, where do we start and what do we include? Well, the first thing that I was thinking of is let's maybe define what this is not going to be about. It is not going to be a complete guide on how to build an RF coil. This is also not going to be a complete overview of every aspect of RF coil design. So we're not going to talk about preamplifiers, we're not going to talk about active and passive detuning or RF shielding. And this is certainly also not going to be a physics lecture on electromagnetism. What this will include is some basic electromagnetism, at least enough to understand the principle of a simple RF coil, to understand some of the common terms that are associated with coils, like tuning and matching, Q value, Q load, etc. And finally, to understand the practical considerations that are involved with using RF coils. So, if you look at a very state-of-the-art RF coil, like shown here, this is the inside of that RF coil. It has many elements, including a preamplifier, balance, matching, tuning, detuning, and we're not going to talk about most of these elements. So this is not really our model coil, if you will. What we are going to talk about is the simplest coil possible, which is basically a surface coil, which basically has a few variable capacitors, a few fixed capacitors, and in reality it also looks like a very simple loop as shown here for the proton nucleus right over there. So this is what we're going to focus on. But even to understand this simple coil, you already need a lot of knowledge, and it's probably unreasonable to assume that everyone has this basic knowledge. So to kind of counteract that, basically I decided, okay, let's make 3 videos for kind of like people with different background, basically different starting points. The first video, which is the current video, is going to cover static effects that include electric charge, electric fields, current and resistance. Then the second video is going to talk about dynamic effects, because radio frequency is of course a more dynamic effect, right? They have time varying alternating currents, we have magnetic fields, we have inductance, we have resonant circuits, and so that is definitely a much bigger step towards radio frequency coils. And then the final video is going to be actually about radio frequency coils, about the practical considerations and many of the aspects associated with RF coils. Okay, so certainly if you're familiar with resistance and voltage and all those kinds of terms, you can easily skip this first video and don't really miss out on anything. And then I hope you will watch video 2 and video 3. So we're going to start with a few axioms, because some things are just very difficult, if not impossible, to explain. We all know that many particles have mass, but mass is actually not super easy to understand. Similarly, those particles typically also have electrical charge. It's another concept that is not easy to understand and to explain. We know that protons have a positive charge and electrons have a negative charge. So mass is difficult to understand, However, we experience mass, and we experience mass because mass generates a gravitational field. And a mass is then experienced as an attractive force in that gravitational field of other masses. So we know that if we have a cup and we let it go, it will fall to the ground because it experiences this attractive force of the gravitational field of the Earth. And that's how we kind of understand mass. Similarly, charge. Charge generates an electric field. And the electric charge is then experienced as a force in the electric field of other charges. However, there is a big difference between mass because the force between two masses is always attractive. Therefore, things always fall down and they don't fall up. However, electric charges can be positive or negative. And if the charges are opposite, then it's an attractive force pulling them together. And if the charges are identical, either negative or both positive, then the force is repulsive and they push the charges away from each other. Now, in pictures like this, the solid black lines represent electric field lines. So there is definitely an electric field around each particle. And you can see that when the field lines are very dense, then the electric field is very strong. Whereas when the electric field lines are very sparse, the electric field is much weaker. Now, there are definitely positive and negatively charged particles. However, for most of the things that we're going to talk about in the coming videos, we are mostly interested in the negatively charged electrons because those are the particles that actually move around. And so we're mostly interested in electrons. And so that means that if we have a uniform plate that is negatively charged, we typically expect that to be because there is an excess of electrons in that plate, and that's why it's negatively charged. Similarly, if we have a plate that is positively charged, that is because there is a deficiency of electrons, making it a positive plate. Now, if you have a positive plate and a negative plate that are very large, then in between you're going to get an electric field that is quite homogeneous, and you can see that from the equidistant field lines. That implies homogeneity. And it's also homogeneous if you now place a particle in this electric field, then that particle will experience a force, and that force will be the same if the particle is here, or if it's there, or if it's there, because the electric field is the same everywhere. Okay, just to move things along, I like to consider a battery. Because a battery is an everyday object, we kind of understand what a battery does, and so I think it demonstrates a few things very nicely. So on a battery, you have a positive side, which is referred to as the cathode, and you have a negative side, which is referred to as the anode. If we now look inside the battery, then there will be again two sides, the positive side and the negative side, and each side has its own unique chemicals. On the positive side, we're going to have so-called reduction reactions that basically consume electrons, and they produce negatively charged hydroxyl groups. Now, this hydroxyl ion is basically entering the space in between the anode and the cathode, and because the concentration of the hydroxyl here is larger than on the anode side, it basically experiences a chemical force due to the concentration field gradient, and the hydroxyl basically migrates towards the anode. On the anode, we have a so-called oxidation reaction that produces electrons. The hydroxyl basically reacts with zinc in this case, and it produces electrons. Now, to balance things out, the electrons could go to the other side, to the cathode, and basically that would balance out both reactions. However, a battery is set up in such a way that it is not possible for these electrons to move to the cathode. So basically the electrons are stuck on the bottom plate, and you're going to get an excess of electrons on the bottom plate and a deficiency of electrons on the top plate. In other words, there's going to be an electric field gradient and an electric field between the two plates. Now, things continue to happen as I just explained. The cathode side is producing hydroxyl groups, hydroxyl ions, and they basically move into the space. they experience a chemical force because of the concentration difference, but now it is a negatively charged ion in an electric field. It also experiences an electric field force. At this point in time, the chemical force is still larger, so the hydroxyl still moves to the anode side, leading to a larger and larger excess of electrons and making the electric field in between the plates stronger and stronger. Now you can of course see where this is going. At some point the electric field is so strong that it perfectly balances the force by the chemical concentration gradient. When these two forces are identical, the hydroxyl ions do not move anymore and basically the reactions stop. And this is what is referred to as a so-called open circuit voltage. Basically, internal to the battery, if you get a nice new battery out of the package, inside of that battery there is an electric field, and on many batteries it is 1.5 volts. And that is because there is a deficiency of electrons on the top plate and an excess of electrons on the bottom plate. Now, what does 1.5 volt, or that's the voltage, mean? That means that there is 1.5 joules of energy available to act on 1 coulomb of electrical charge. Okay, so this really illustrates quite a few things, right? That internal to the battery we have an electric field, but the electrons are basically stuck on the bottom plate and they cannot move. Now, things get more interesting, of course, if we connect a copper wire to it. For now, let's leave the circuit or the copper wire open. So basically nothing happens. It's still going to have your 1.5 volts internal to the battery and nothing else happens. If we quickly look into the actual copper wire, then inside the wire we have the copper atoms, and those really are not moving. They're basically stationary. The electrons are very loosely bound to the copper and they tend to move around quite a bit. They move around at a Fermi velocity, which is about 1500 kilometers per second, which is quite fast. However, this is random. They are in a random orientation, and so basically there is no net movement of electrons. The net movement is 0. So while this happens, we don't really have to consider it any further, and from now on I'm going to ignore this random motion even though it is there. So now things get of course more interesting if we close this circuit, right? Before the circuit was closed, we had the electric field internal to the battery, but the electrons were stuck. However, now we're going to be having a new path available for the electrons to move. Rather than going up inside the battery, they can go down through the wire to the other side. Now that's exactly what's happening. As soon as this circuit is closed, the electric field is also being set up inside the copper wire. Inside the wire there is an electric field. And so now we have the force and the path available for the electrons to move around the wire. Notice that the electric field is actually set up very, very, very fast. As soon as this closes, the electric field is set up at almost the light speed. In copper wire it's about 2/3 of the light speed, but it's very, very, very fast. The electrons, on the other hand, they don't move that fast. Very often you see pictures like this where the electron, now there's an electric field here and there is a closed path so the electrons can go around. However, the electron doesn't go all the way around as shown here because electrons actually don't move that fast. If we again look at a cross section of the wire here, these are a bunch of these electrons. They all move in unison, which is good because that gives you your electrical current, but they actually don't move that much. For typical electrical fields, the so-called electron drift velocity, that is the speed at which they all moved in unison, is measured in millimeters per second. Now, the electron drift velocity does scale with the electric field, so if your electric field is 10 times as strong, the drift velocity will be 10 times as fast, but still we're measuring things in like millimeters per second. So electrons that are here in the wire, they will most likely never make it all the way to the other side. They just don't move that fast. Okay, a few words about electrical current and movement of electrons. So we already know that the electrons are moving from the anode to the cathode. However, classically, the electrical current is defined as going from the positive side to the negative side. It doesn't really matter, it's just good to be aware of this difference in motion. So now we know a few terms. We know electrical current. Electrical current is basically the amount of charge that flows past a given point per second, and the unit is in ampere. That means if I measure the amount of electrons flowing by this point here per second, or over there, that current is the same at all locations. Voltage is basically the electric potential energy that is available to work on charges. The unit is in voltage, which is also joule per coulomb, energy per charge. And then finally you have the resistance, which is basically the opposition to that electrical current. Or in other words, it is the amount of energy that is needed to push the current around the given circuit, and it's expressed in units of ohm. Now there's a very simple relationship, whereas the resistance is the voltage divided by the current. Now what is important to realize is that for a given DC, so direct current, for a given DC current, the current is constant everywhere. As I mentioned before, if you measure there, or there, or there, or there, you're going to measure the same flow of electrons per second. The voltage and the resistance can have local variations in such a way as to make the current constant. So how does that then work? So let's have a look at a copper wire. This is a cut through that. And let's say in this copper wire we have the electric field because the battery is attached, and we have the electrons in blue. And at this point, in this measurement point, we basically measure 4 charges moving past this point per 1 second. So that's our current. The cross-sectional area of the wire is A, and the speed at which the electrons move is the drift velocity. Now let's now say that further down the wire narrows a little bit. Well, we already mentioned that the current needs to stay the same, because if the current is not the same, you're going to get accumulation of electrons right here, and you're going to get a deficiency of electrons right there. That doesn't happen in reality. In reality, the current is constant throughout the entire wire. So how can we achieve that? If we measure here, that means that at this point where the wire is narrow and cross-sectional area is 4 times smaller, the only way to keep the same current is to make the drift velocity 4 times as high. The electrons need to move 4 times as fast past this point to keep the same overall current. Now, how do you make the drift velocity 4 times larger? By making the electric field 4 times larger. And so that's where the voltage comes into play. Between this point and this point, the voltage only drops a little bit, because there's only a small electric field. But then when the narrowing comes, you're going to get a huge drop in voltage because the resistance also goes up, and that leads to an increase in the electric field, that leads to an increase in the drift velocity, all to maintain a constant current throughout the entire circuit. So this is all I wanted to say in this first video. It's a very basic video about basically voltage, current and resistance, and that also represents the most basic electronic circuit, which is an interplay between these 3 parameters. Many electrical effects can be explained with purely electrostatic forces that then lead to a motion of the electrons. But however, we can see in the next video that for radio frequency coils, we also need to consider things outside of the wire, dynamic effects, and then electrostatic forces aren't sufficient. The voltage or the voltage drop or voltage difference, that provides the electric field and the associated electric force needed to propel the electrons forward, and then those moving electrons then form the electrical current. Resistance is a scaling factor between voltage and current, and it expresses the amount of energy per charge that is required to push those electrons around the circuit. The drift velocity of electrons is typically quite small. It's measured in millimeters per second or even less. There is a much larger random movement given by the Fermi velocity, but most of the time we can ignore that. And perhaps most important is that the electric field and the electrical signals, they do propagate at near speed of light speeds. Finally, I think an electric circuit can at this point in time be seen as an energy conversion system in which the potential electrical energy, due to the position of charge in the electric field, is converted to other forms of energy, like heat, mechanical or radiant. Now, as I mentioned before, this is a very, very basic video. This was really meant for those of you who don't have much of a knowledge on basic electrical properties. And hopefully this will, give you a good introduction for the next two videos, which are much, much closer to where we want to be talking about radio frequency coils. This is me, Robin de Graaf. You can always talk to me at meetings if you see me. You can also email me, of course. And some of this material is also covered in this book. And with that, I hope that you're still interested and go and see videos 2 and videos 3. Okay, thank you.